Welcome back to the Foundry by Forge College. Okay, if you were hanging out with us in the previous explainer, the one on mapping deployment workflows and checklists, we definitely left some blank spaces in our plans, vague placeholders. Well, today, as we continue our journey through our Solana deployment fundamentals, we're transitioning those vague placeholders into cold, hard facts. We're going to blueprint a tool to spit out real numbers so you can confidently hit that deploy button without, accidentally draining your entire life savings on a single test transaction.
Let's check the blueprints for today's explainer to see exactly how we'll build out these estimates step by step. We are covering 1. Moving from placeholders to concrete estimates, 2. Storage rent versus compute fees, 3. Blueprinting the Python estimator, 4. Running the estimation math, 5. The 10% checkpoint, and 6. Updating your deployment checklist.
Section 1. From placeholders to concrete estimates.
Remember those vague placeholders from our last lesson, like allocate X compute? Well, a placeholder definitely won't pay your network fees. What actually happens when you push to mainnet without running the math first? It's literally like building a house without a budget. You hire a crew, break ground, and halfway through pouring the foundation, your wallet is completely empty. On the blockchain, a blown budget means failed transactions, frozen state initialization, and honestly, a severely stressed out developer staring at an error screen, highly likely to end in tears.
Section 2. Storage rent versus compute fees.
Okay, to estimate properly, you really have to understand the two main cost beasts you'll encounter on the Solana cluster: storage and compute. Think of it this way. Storage is like renting a long-term apartment for your data. When you initialize an account, it takes up valuable real estate, and it stays there. Compute, on the other hand, that's like paying a short-term contractor for their immediate labor. It's the one-off cost of validating signatures and executing logic.
Let's define compute units precisely. So every single time your program executes an instruction, whether that's serializing data, verifying a hash, or making cross-program invocations, it burns compute units. And here's the kicker. Solana strictly caps the amount of compute a single transaction can use. If you demand too much labor, the network contractor basically just drops their tools, walks away, and your transaction fails.
And then we have the rent-exempt balance. This is the minimum lamport deposit required to keep an account's data alive, or rented, on the blockchain. Basically, if you want your account to stay active, you have to deposit a minimum amount of native tokens based on the exact byte size of your account. It's a security measure to prevent state bloat on the network. Just think of it as a security deposit that ensures your data's real estate lease stays active and doesn't get evicted.
All right, moving on to Section 3, Blueprinting the Python estimator.
Grab your technical pens, because we're drafting a minimalist Python script to calculate these exact costs. We need some core inputs to feed into it. Say we're deploying a small program. We'll need to create 3 accounts, let's say at 1,024 bytes each. For the labor, we estimate 40 instructions per initialization, batched across 4 transactions. These are your essential puzzle pieces.
We'll feed these inputs into our script alongside some conservative constants, or if you want to get fancy, optional RPC lookups to calculate realistic totals. For your first draft, you can just use hard-coded constants, like estimating a standard rent rate of 3,480 lamports per byte year and an average of 200 compute units per instruction. Once you're comfortable with that, you can actually level up by hooking the script directly into a Solana RPC node that fetches live, real-time data straight from the cluster for absolute pinpoint accuracy.
Section 4. Running the estimation math.
We have our blueprints. Now let's run the engine and see how this builds our concrete estimates. What's actually beautifully simple here is the math. For storage, 3 accounts times 1,024 bytes is exactly 3,072 bytes of real estate. Multiply that by our rent rate constant, and we need a deposit of about 10.6 million lamports. Boom! Suddenly that vague placeholder is a mathematical certainty. Now for the labor side. 40 instructions multiplied by 4 transactions at an average of 200 compute units gives us a 32,000 budget. This right here is your compute ceiling. If you run your tests and find out you're actually burning, say, 100,000 compute units, well, you immediately know you have a major architectural problem to solve before you ever even think about touching mainnet.
Section 5, the 10% checkpoint. A good engineer always calibrates their instruments. We must cross-reference our manual hand math against the Python script's output to verify the numbers match within a strict 10% margin. Seriously, grab a calculator. If your script says 1 billion lamports and your hand math says 10 million, something is horribly wrong. Maybe you multiplied by an extra factor, or maybe your input JSON is formatting numbers as strings. You only pass this checkpoint when the human and the machine agree. But what do you do if your script reveals that your chosen approach is wildly too expensive? Let's say your script works perfectly, but it tells you that your current architecture is going to cost an absolute fortune in rent, or it's going to blow right past the compute limits of a single transaction. Well, this is exactly why we estimate before we deploy.
Don't panic. Just follow our mitigation trio. Step 1, compress the account layout. Look closely at your data structures. Can you pack your variables tighter? Step 2, increase transaction batching. And step 3, split the state initialization across multiple smaller transactions so you don't smash into that compute ceiling. This right here, this is where real engineering actually happens.
Section 6. Updating your deployment checklist.
Armed with accurate, tested numbers, we can finally update our deployment playbooks. You're going to directly integrate these estimates into your checklist, replacing those original, vague placeholders with concrete, actionable rollback thresholds. Instead of writing something unhelpful like check if compute is okay, your checklist will now explicitly say, if transaction exceeds 32,000 compute units during dry run, initiate rollback. You're no longer guessing. You've established cost-aware validation criteria that'll catch catastrophic errors in testnet before they ever reach production.
So the crucial takeaway here is this. Treat storage and compute as completely separate planning dimensions. They are the twin pillars of resource management on Solana. One impacts the persistence and rent of your data lifecycle, while the other dictates the immediate execution constraints of your transactions. Keep them separate in your mind and estimate them separately in your scripts.
With your estimates locked in, you possess a repeatable, automated tool that replaces anxiety with hard data. You know your bytes, you know your lamports, and you know your absolute compute limits. So the question is, are your resources fully calibrated for the cluster? Are you ready to push? Before you finalize your playbook, test your absolute worst-case scenarios. Because in Web3, inefficient code doesn't just run slowly, it literally drains the network's liquidity. If every single byte has a price tag, how much is your sloppy architecture really costing you? Head over to forge.college to master these concepts, dive deeper into our Introduction to Solana deployment courses, and explore other incredible Web3 topics. Keep calibrating those numbers, stay curious, and I'll catch you in the next explainer.